Lesson 4.4, Angular and Linear Speed. We'll now explore an application of trigonometric properties in relation to angular and linear speed. All of the information you need to know about the topic is contained within the following exploration. So, Exploration 441, Angular and Linear Speed. Can you feel the breeze? The coordinates of Austin, Texas are 30.27 degrees north. We're going to need that. 97.76 degrees west. Using 3960 miles as the radius of the Earth, we want to find the linear speed of a person living in Austin with respect to the center of the Earth in miles per hour. In answering the question, we'll consider linear speed, v sub 1, to be the distance traveled along an arc, the arc length, s, per unit of time, t. So linear speed, v sub 1, is equal to s over t. We'll also consider angular speed, this little w, that's omega, to be the radians traveled that correspond to the arc length theta per unit of time t. So angular speed is omega equals theta divided by t. Background. Number 1, write an equation for linear speed, v sub 1, in terms of angular speed, omega, using the fact that the arc length is equal to the radius of the circle r times the angle theta, corresponding to the arc. So here's our third equation, s is equal to r times theta. So you'll need to use these three equations to finish the exploration and also for your homework and your quizzes. So we want to write the equation for linear speed in terms of angular speed. Well, the first thing that I can do is I can make a substitution for s. S is equal to r times theta. So my first move would go ahead and rewrite s as r times theta. Now, my second substitution, I can rewrite theta over t as omega. So this is going to equal r times omega. So linear speed in terms of angular speed, v sub 1 is equal to r times omega. All right, before we attempt to answer the title question, let's first consider a slightly simpler question. We'll consider a merry-go-round, a circle, spinning around an axis rather than the Earth, which is a sphere. So suppose a merry-go-round has a diameter of 10 feet and revolves once per minute. Find the angular speed of the merry-go-round in radians per minute. So the angular speed is equal to theta divided by time. And theta, one revolution, is 2 pi radians, and the time is 1 minute. So the angular speed is 2 pi radians per minute. If Olivia is standing 3 feet from the center of the merry-go-round, her radius is 3. What distance does she travel in 1 revolution? Well, we're trying to find arc length for Olivia, which is just radius times theta. 1 revolution is 2 pi radians, and so this is 6 pi. And this is the distance. Distance is measured in feet. And I don't know what 6 pi is, but I can approximate this at about 19 feet. That's how far she travels every revolution. If Olivia is standing 4 feet from the center, that's her radius. What distance does she travel in 1 revolution? So the arc length that Libby travels is 4 times 2 pi, which is 8 pi feet, and that is approximately 25 feet every revolution. Who is traveling faster, Olivia or Libby? Well, I can say that Olivia travels 19 feet every revolution, while Libby travels 25 feet per revolution. So I can say that Libby travels faster. And that is because she has further to travel in the same amount of time. Okay, so is there a place where the linear speed of a person on the merry-go-round is 0 feet per minute? Well, let's think about that. Every revolution, you are not traveling at all. Well, you'd be standing at the center. Of the merry-go-round. And where should a person stand so they have the fastest linear speed? Well, I would be holding on to the very edge or the circumference of the merry-go-round. So to answer this question, where should a person stand? On the circumference of the merry-go-round. So now let's take a look at the Earth. What is the angular speed of the Earth in radians per hour? Well, the angular speed of the Earth travels through 2 pi radians in 24 hours. And so if I reduce this, this is pi radians, or pi over 12 radians per hour. Suppose Libby lives in Pontiac, Indonesia, right on the equator. So I'm going to draw a picture of this. Here's my Earth. Here's my equator. And I'm going to put Libby right here. What is Libby's linear speed with respect to the center of the Earth in miles per hour? Okay, so Libby is right here on the equator, and she's traveling on this circle, this circumference, right? This circle. How fast is she going? Because that's what the question's asking. What is Libby's linear speed? Well, linear speed is equal to r times omega. The radius that Libby lives on is the 3,960. That was given in the opening part of the problem. And omega we found in question number 7, that is 12 over pi. And if I were to multiply these out, let's see, 3960 times 12 over pi. I don't think I'd work that. She is, oh man, I just did that backwards. How about pi over 12? I'm like, what? I got a totally different answer than I did before. There we go. How about that? 3960 times pi over 12 is 1036.73. And this is miles per hour. So that's how fast Libby is traveling with respect to the center of the Earth. Is there a place on the Earth where a person has a linear speed of 0? So now, when we were on the merry-go-round, if you were standing at the center, you are not traveling any distance every revolution. Well, where would I stand if I was on the Earth? How about at one of the poles? Either the North or the South Pole. Every revolution, you're not traveling any distance. So I would say at one of the poles. And just every revolution, you're not traveling any distance. Suppose Olivia lives in Austin. So now let's put Olivia like right here. That's Austin. Do you think Olivia has the same linear speed? Well, I'm going to guess no, because I can see that her circumference, her circle, is smaller than Libby's. So do I think they have the same linear speed? No. And that is because Olivia travels in a less distance than Libby in the same amount of time. Question 11, find the radius of the latitudinal circle on which Olivia and Austin travels. Okay, so we want to find the radius of the circle that Olivia travels. All right, so that's this guy right here. This is going to be my x. So let's use what we've been given. We know that the radius of the Earth from the center of the Earth to Olivia, this is one radius. This is 3,960. I'm going to go ahead and miles. Okay, now we also know that Austin is at 30.27 degrees north. This angle here is 30.27 degrees north. I can draw in a right triangle because we're going to say that her radius is going to be perpendicular to the pole or to the center vertical axis on which the Earth spins. And if the angle on the exterior is 30.27, I can say that its complementary angle is, let's see, well, 90 minus 30.27. I think I already calculated that. Yes, 59.73. The angle on the inside is 59.73 degrees. I can use some right triangle trig to figure out Olivia's radius. So from the angle to Olivia, that's going to give me the opposite side, and I know the hypotenuse is 3960. It's across the right angle. So opposite and hypotenuse is the ratio of sine. So sine of my angle is equal to opposite over hypotenuse. And if I solve for x, 3960 times sine 5973 is equal to x. Now I've already put this in my Desmos, so I just need to check it. 3960 times sine 5973 is 3,420.09 approximately. So her radius is 3,420.09 miles. All right, so Libby, living on the equator, is at the center of the Earth. I'm sorry, the radius is 3,960. So Libby's radius is bigger than Olivia's radius. And so in question 12, find Olivia's linear speed. Linear speed is equal to radius times omega. And if I calculate this out, 3420.09 times pi over 12. I think I already did that, 3420 pi over 12. Yeah, 895.37 or 38. Oops. Miles per hour, approximately. All right, so now, did you guess correctly? Well, we know that Libby is traveling at 1,036.73 miles per hour, and Olivia is traveling at 895.38 miles per hour. So I guess correctly, Libby is traveling faster. Oh, I guess I didn't write it down from the previous. Is she going faster or slower? Well, Olivia travels less distance than Libby in the same, so I was guessing that Libby was traveling faster. So yes, I guessed correctly. You should have found that Olivia and Libby are going very fast, twice as fast as an airplane. Why don't we feel a breeze as a result of the Earth's rotation? Well, it's all about the frame of reference. If everything around you is also moving at the same linear speed, then you're not going to notice that speed that you're traveling. All right, so that is it for this exploration.